Okay, let's go over Fermat's theorem, which is used in calculus. And it's simply saying if you have a continuous function, that means that you can draw from A to B on a piece of paper without lifting your pencil. And if it's differentiable, it means there's no kinks, it's smooth. That means the derivative or the slope of that function is going to be at that optimal point will be equal to 0. The slope is 0 at a maximum or minimum, local maximum minimum. So let's prove that. So I'm going to start talking about Fermat's. Let me see if I can do this here. Change the template. So I can go there we go. Fermat's. Then we have this theorem. And what does it state? Well, it says if this function, if f, let's say f of x, has what we call a local minimum, that means within the middle of some range of numbers, which we call the domain, that f of x has a local minimum or maximum, right? And if f prime evaluated at c, the derivative evaluated at c, and we're going to say that exists. If that exists, then what I'd like to show is that f prime of c evaluated is equal to 0. So that's really not a big deal. It's simply saying that if I have something, a function, and it's from, let's say, from A to B, okay, and though this thing goes something like this, let's say. So what it's saying, somewhere along here you can find a C, such that when you find the slope of the tangent line, then that would be the slope, would be the derivative of the function itself, evaluated C will be equal to 0, you see, and that is a slope equal to 0 for that tangent line. That's what we're trying to show. And so this would be something like y and x, right? So the way to do that is, let's suppose that at C we have a local, let's say we have a local maximum. So I think you can see that if I have f of c, right, and I'm saying f of c, well, it's a maximum at that point. If it's a maximum, we say, okay, then that will be greater than a little bit moved away from c, that's c plus h. You see, so if I do some subtracting there, I'll have 0 is greater than or equal to f of c plus a little bit, ch, minus f of c. That's just the algebra, right? And in that case, what I can do is say, all right, now I'm going to take that thing right there and divide both sides by h, which is perfectly allowed. I'm setting up that, really it's like a rise over the run, isn't it? Where h is a little movement on the x, and f of x, c plus h, and this thing is kind of like the rise, right? And this is sort of the run of a slope. So we have that and that. So now if I take a look at the limit, so if I take the limit now, definitional limit, as h goes to 0 of a constant, well, 0 is a constant. It's just a constant because the 0 is not changing with h. Okay, but here, the limit as h goes to 0, let's say from the right of this right here, f of c plus h minus f of c, right? And then I have to be careful, this is greater than, right? Greater than equal to, let's clear that up a little bit. Okay, so that's like that, right? And that's going to be f of c, right? And that's going to be over h. And we were given, right, that f prime of c exists. So that means this limit must exist. So what we have is the limit of that just 0 is less than or equal to, and that is f prime of c. So it's saying if we come in from the right, then the derivative of c will be always greater than or equal to 0. Now, if we take a look at it again and say, suppose we have the case that h is negative, so we're going to have that h is less than 0. So if h is less than 0, it's a negative number, right? So we can say that we can keep the same thing, but take a look at what happens here. So let me just go here. So if I have 0 and then is less than or equal to f of c plus h, and then minus f of c, and that's over h. And remember, I'm saying it's less than 0. So I'm just going to simply multiply this guy here by minus 1 and this guy here by minus 1, see? And if I do that, well, that's just going to be 0, correct? And, well, I got it. I multiply by minus 1, right? But h is negative anyway, so that makes it positive, right? So that'll take care of the negative, but this thing will switch once I multiply both sides so that I get back to where it was. F of c plus h minus f of c over h. And if I take the limit as h goes to 0, right? That means that means that this part will be equal to f prime of c, right? So using this 0 here, I have, see, 0 is greater than or equal to f prime of c. So we have kind of a squeeze theorem, because on the one hand, you can see that what we have from the very first thing, right? I got it right here. Let me put it in green. Then I'm showing this, right? So I'm showing that f, in this case, f prime of c, right, is greater than or equal to 0. And then, and over here, I'm showing that 0 is greater than f prime of c. Well, you can see that the only way that can happen, let me clear that up a little bit here, because it doesn't look good. So I'm just simply saying that if I go here, so I'm saying that in this case, okay, 0 is greater than or equal, that's right here in this case, f prime of c. But in this case, 0 is also less than or equal to f prime of c. Let me straighten that up a little bit. I'm taking that from here, where f prime of c is greater than or equal to 0. See it? That's what that says. And then this one says, but 0 is greater than f and c. So this part is right here, and this part's right here. And that can only happen if you sandwich, kind of squeeze it down. That means it can only happen if f prime of c is equal to 0. And that's what we wanted to prove.